Hi, it's Mr. Andersen, and this is AP Physics Essentials, video 83. It's on work and power. Work is applying a force for a given distance, and power is how quickly we do that work. And so let's say I want to lift these identical crates to the top of a room, and I use two different motors, we'll say A and B. You can see that A goes much quicker than B does. And so a question you might be asked is, which one did more work? So since we're overcoming the force due to gravity, it's the same force over the same distance, and so they both did the same amount of work. Now, which one has more power? Since the one on the left did that work more quickly, it's going to have more power. And that's why it's important to measure not only how much work is being done, but how quickly that work is being done. So work is the amount of energy that we add into a system through an external force. Now, if we just apply a force, but there's no motion within the system or the object, no work is done. We have to move it a given distance. But once we do that, work is equal to the force applied times the distance we move the object. And we're going to measure that in joules. It's the amount of work we're doing on the system. Now, we could have moved it more quickly, and so another measurement is power. Power is simply the change in work over the change in time. If we move it more quickly, then we have a higher power. And so work is applying a force to an object to move it a given distance. So when this pitcher throws the ball, he's doing work on the ball. And so what are the two things that we need? We need to have a force and we need to have a distance. And those two things have to be in the same exact direction. And so the force has to be parallel to the direction in which we're moving it. And so thinking of those two things, let me give you some examples. And again, in the video, you could always pause it, try to work this problem before I show you what the right answer is. So let's say we apply a 6 Newton force on a box in the horizontal and the box doesn't move. So how much work did we do? Well, it's equal to the force parallel times the distance. What was the force? 6 newtons. What's the distance? It didn't move. And so that's 0 meters. And so how much work did we do on an object? It's going to be 0 joules. Even though we're applying a force to it, if it doesn't move, then we don't do any work. And this is how work is different in science to the way we think about work just in the regular world. Let's try another problem. Let's say I apply a 16 Newton force to an object and I move it 2 meters. Could you calculate the work? Well, again, work is equal to force parallel times distance. What's my force? 16 newtons. What's my distance? 2 meters. And so that's going to be 32 joules of work that I've done on that box. Let's try a more difficult problem. Now I'm applying 16 Newton force, but it's at a 45-degree angle to the motion in which the box is moving. So we still move it 2.0 meters. How would you figure out the work now? Well, we have to make sure that that force is parallel. And so we're going to use a little trigonometry. So what we really need is this adjacent force right here, this force in the parallel. So to solve that, it's 16 newtons times the cosine of 45, because the cosine of 45 is equal to that adjacent side of this triangle times the hypotenuse. And so now I get, with significant digits, 23 joules of work that I'm putting into that box. Now let's look at a box like this. And so I'm applying a 2.5 Newton force up, and I'm moving it in the horizontal. So how much work am I doing on that box? Well, the force and the direction have to be in the same direction. And so my direction is not in the direction of the force, and so my work is going to be 0 because we're not applying that force in the direction that we're moving it. Now, what's power? Power is going to be the change in work over a given period of time. So let's do this problem again. 16 Newton force, 2 meters, and let's say it takes me about 3 seconds to move it, so 32 joules. 3 seconds, so how do I figure out my power? It's simply the change in work over the change in time. So it'd be 32 over 3, and so I'm going to have 11 watts of power. Let's say I do the same exact thing, but this time I'm moving it more quickly. It's 0.5 seconds, and we're going to have more power or less power. Well, I'm going to have more power to do that. Since I'm dividing by a smaller number, it's going to be 64 watts. And so when you're looking at a light bulb that's a 60-watt light bulb, it's a measure of the power, how much work it could do in a given period of time. And it's named after James Watt. So how could you measure this in the physics lab? You could hook up a spring scale to an object, pull it a given distance. If we know the force and the distance it's moving, we could figure out the work. We could even hook up a force sensor that's measuring forces over time or over distance, and we could graph it like that. So we've got a 2 Newton force, you could see, over 0.6 meters. And so how do I figure out my work? It's just force times distance. But since we have it on a graph, what's neat is I can simply calculate the area under that curve, and that's going to tell me the amount of work that I've done. And even if I apply with different forces over time over that distance, all we have to do is figure out the area under that curve of a force versus distance curve, and that's going to tell me the amount of work. So without using calculus, we could just break it into these different little shapes and figure out the amount of work that we're doing. Now, James Watt knew this, and he was able to apply it to pressure and volume. And so in a mechanical system, it's a force applied over a given distance. But if we're looking at a gas, for example, as we compress a gas or release a gas, our curve is actually going to be the pressure versus volume curve. And he and his fellow worker, Jonathan Southern, came up with this really brilliant idea on how to do that. They took a piston inside a cylinder here, and they had a pressure gauge on it with a pencil, and as they moved that piston down, it measured not only the volume inside the piston, but also the amount of pressure on there. And so he was able to make a piston that was perfectly calibrated, so he wasn't moving it and not doing work, because the area under that curve is going to be the amount of work that we actually do. So did you learn to calculate work in the lab? All you do is measure the force over a given distance. Could you use a force versus distance graph to calculate the area under the curve, telling you the amount of work that you've done? And do you know that the amount of work being done is equal to the amount of energy that were added to the system? And then finally, in AP Physics 2, do you know that that force versus distance graph, if we're dealing with a gas, is going to be a pressure versus volume curve? I hope so, and I hope that was helpful.